Okay, we're gonna talk about the carbon cycle some more. And this this lecture is based on pages 158 to 161. And you can skip a few pages and continue on in Comp. It's I think chapter 8. So just to review a bit, if we're interested in changes in the CO2 concentrations in the atmosphere, it's sort of the main focus. Today we're going to look at the long-term geologic changes. But in any case, they are, just as a reminder, it's the difference between how fast we're losing CO2 versus how fast it's being produced. So that's going to determine how it changes. And another reminder, we're going to have 4 here. So carbon bonds with other elements. Forming many different compounds. And, right, so it's in the atmosphere, it's connected to oxygen, but then, when it gets breathed in and turned into plant matter, it's attached to hydrogen and other elements depending on where it is in the cycle. So it moves then through the Earth system as these different compounds. However, the total amount of carbon on the planet, on or in the planet, is constant relatively. I suppose that we gain a little bit from asteroids, but it's not a significant enough amount to worry about. So this is basically, we're generally gonna, when we zoom out, especially to the geologic time scale, the long-term scale, we're going to be thinking of carbon as a cycle as a closed system. So we're not going to have sinks and sources. Okay. So the long-term carbon cycle, or cycles actually, we'll be talking about different aspects of it. So if you look at, let's start with the question, basically, why is there CO2 in the air at all? You could say, still. Basically, it means that it has to mean that the short-term processes involving CO2 being produced and consumed, they mostly balance. Otherwise, we'd quickly run out, or there would be go to extreme levels. So if you think about, like, the ocean, for example, has 900 gigatons of carbon. So if we were losing 1 gigaton a year somehow by processes not balancing, in 1,000 years it'd all be gone, right? So somehow the short-term processes roughly balance, and on a longer term scale, if we look at a plot of carbon dioxide, CO2 in the atmosphere versus time, and we're going to measure this in millions of years ago. So this will be today on the right, and we'll start about the time that multicellular life that that we would recognize, animals, appeared around 600 million years ago. And on this scale, we're going to measure this in ppm. So you might remember we're sort of in the low 400s these days, but we're actually going to measure this scale in the thousands, 4,000 and 8,000. So the history of carbon dioxide looks something like this. It was very high, and it's kind of come down more recently. This isn't quite as dramatic a peak as I showed there. Okay, so beginning with this is called the Cambrian explosion, when all this interesting life appeared. So over the geologic timescale, carbon dioxide has been far higher than it is now, more than 10 times as high. And basically, the story here, where did all this carbon dioxide in the air go? A lot of it ended up in the rocks, deposited in the rock layers. And what we're doing now as humans is we're kind of digging that out and putting it back. So it's understood that the proliferation of life overall has drawn down CO2. It's put a lot of organic carbon has been buried, but at the same time, other long-term processes that we need to be aware of is that CO2 is being released by volcanoes, and that's been going on for even longer than that, for billions of years. So basically, the volcanoes keep pumping it into the air, and life has, in a relatively short amount of time, put a lot of that back down into the crust. So another important point about the long-term carbon cycle is that the fluxes are small. And they're small because they involve geologic processes. So if you think back to those diagrams of the oceanic or the terrestrial carbon cycle, we had fluxes that were, on the order of 10 gigatons per year. So these geologic processes, sedimentation, for example, are released from volcanoes are typically more like a tenth of a ppm per year. So they operate over thousands to millions of years. So we'll talk about a number of these next. So this one we've alluded to before, sedimentary rock formation. So we talked about how in the bottom of the ocean um, there's sedimentation, and over time it's a process called lithification. The sediments can turn into rock. There's a constant flux of sediments that carry carbon to the seafloor. So, think about like all the shells that you find at the beach. So it's just kind of getting washed down and piling up year after year. Not to mention, much more significant, the accumulation of all those microorganisms that we talked about. So progressive burial leads to lithification. It's like turning into a rock. So the sediment turning into rock. And this creates the largest reservoir of carbon on the planet. To the 7 gigatons. Most of that is a rock called shale, which is basically, it used to be mud. The mantle also has a lot of carbon, sort of in this range. It's not as well known exactly how much. Okay, so a specific sort of subcategory here is fossil fuels. So fossil fuels are when the carbon is in such high concentrations that we can light it on fire, basically. So high concentrations of plants. So depending on where the carbon accumulates, if it's on land, it turns into peat, and that with higher pressure and temperature can turn into coal. And similarly, high concentrations of organic matter, mostly those microorganisms, in the oceans, in marine sediments, turn into oil. And the difference, that's mainly they turn, part of the reason they turn into one of those versus the other is they're really dealing with sort of a different starting material. So plants, it's the cellulose, and for the oil, it's a plankton. So that's an important part of why we get those two different fossil fuels. Most of the time, the sedimentary rocks, though, are less than 1% carbon. Let's say mostly less than 1% carbon in sedimentary rocks, which means it's not worth it. It's not economic to use that as fuel. So we could do a little. We could draw a diagram. So we could put everything from before, the short-term carbon. So this is This would be the atmosphere, biosphere, ocean, sediment. Let's put that all in one box. And there's a flux into sedimentary rocks. So this box has something like 45,000 gigatons, and this one something like 10 million. And the process here is lithification. And the rate is something like a tenth of a gigaton per year. Right. So, but this is going to balance, right? So it balances by another process that we've mentioned. We'll get into more detail. It's called weathering. And occurs at a similar rate. So basically, there's different forms of weathering, but in a simple form, you simply have bits of organic carbon that are stuck on the rock, and when that rock breaks down, they're released back into the rivers, the oceans, and they end up in this stock. And you could, if we were to add, if we think about, well, some of these said rocks are fossil fuels. What we're doing as humans is we're doing the same thing as the weathering here. But let's call it burning fossil fuels. And we're doing that at a rate more like 6.5. Okay, so humans aren't really doing anything much different than the natural cycle would happen anyway, except we're doing it something like 2 orders of magnitude faster, right? So it's taking things out of the balance. So let's talk about weathering in more detail. So we mentioned organic and inorganic carbon. We're gonna split this down into those types. So we'll start with inorganic carbon. Okay, so there's CO2 in the air. And as we talked about, when the CO2 is mixed with water in the oceans or also in the rain, it creates a weak acid or a dilute acid that dissolves rock. And for the purposes of thinking about this, there's basically 2 types of rock. in the crust. We have what we call silicates. So these have some formula and some SiO2. And so this is most rocks on the surface. This includes granite, basalt, sandstone, shale, and we also have carbonates. So these have a different formula. Instead of ending in silica dioxide, they end with carbon, CO3. That's why they're called carbonates. So this includes limestone, marble, which is just metamorphosed limestone, dolostone, which is similar to limestone but has some magnesium. Basically, these are all things that were formed from shells, which have the formula calcium, CaCO3. So when we have one of these rocks, it has this formula calcium, carbon, and 3 oxygen. Let's write out a formula here. So if we have one of these rocks, carbonate, we add this water CO2 acid. So this is just H2O plus CO2, right? But in this form, we call it carbonic acid. So that reacts to liberate the calcium and form, it's called a bicarbonate ion. So it's basically, what is a bicarbonate ion? It's basically some hydrogen. Let's see if this balances. Right now we have two hydrogen here, 2 hydrogen there. So on this side we have rocks, water, and CO2. And over here we have, erase this. We have some calcium, water, and let's be clear, we have 1 CO2 and we have 1 CO2 here. So what ends up happening, sorry about that, is that the calcium gets used pretty quickly to create more shells, and the calcium dissolved in the water, which basically just reverses this equation. And since we have 1 CO2 on each side, it doesn't really affect, this doesn't affect atmospheric CO2 much. However, so this was for the weathering of carbonates. Let's talk about the weathering of silicates now. So this was carbonate weathering. Let's talk about silicate weathering. So here, a silicate, a typical silicate might have a formula like this: calcium SiO3. So when we combine that with, in this case, we're gonna combine it with 2 of these carbonic acids. It's going to produce, again, it's going to produce calcium. It's also going to produce the bicarbonate. It's going to produce some silica and some water. What's important here, though, is if you look at the carbon, because we're talking about the carbon cycle, right? We have, we have a silicate, rock, water, basically, and 2 CO2s. Important. And over here, the calcium is going to get used to make shells. That's the CaCO3. So we have basically shells, quartz, that's SiO2 is quartz, some water, and one carbon dioxide. Okay, so this is important here. Here it balanced in terms of carbon dioxide. Here where the process of the silicate weathering reduces the CO2. I don't know why I have a parentheses there. So, important message here, silicate weathering combined with the formation of shells draws down carbon dioxide. So that feedback loop that we talked about in an earlier lecture that involved weathering, that was the weathering that sort of matters in terms of the carbon cycle is this one. The most. Sorry, I'm trying to move my... Here we go. Okay, there's still one more kind of weathering to talk about, though. That is the weathering of organic carbon. So here we're going back and talking about the little bits of organic carbon, like diluted fossil fuels that are in rocks. So for that, it's an oxidation process. Which uses up oxygen in the atmosphere and produces CO2. So this is the same process. Let's just write that down. Same basic chemical process as respiration, combustion. So it's basically the slow motion, natural burning of fossil fuels. It's the same. This is weathering of organic carbon is the same thing that we're doing. So if we just back up here, right? Like I said here, this would be weathering. We should modify this. This is weathering of organic carbon. Okay, it's doing the same thing as burning up fossil fuels. So what we've just added to here is the different kind of weathering. This is silicate weathering. It does the opposite. Combined, if we have silicate weathering combined with shell formation, we're taking carbon out of here. I guess silicate weathering, shell formation, and we should add lithification. So the other process that we need to talk about for the long-term carbon cycle is metamorphism. And this is related to the volcanism that I talked about earlier. So when rocks are heated and pressurized, they can release carbon dioxide. So for example, this is part of when rocks are subducted. They experience increasing temperatures and pressures. And that carbon dioxide comes out of volcanoes and springs. So the reaction there is we'll take our limestone formula, or calcium carbonate, our same formation, same formula for shells. It combines with silica, like for example quartz, and they'll form a metamorphic mineral, different metamorphic minerals, but for simplicity we'll use this one called wollastonite. And that releases 2 carbon dioxides. So here we have basically the mineral calcite, quartz, turning into a silicate mineral, and 2 carbon dioxides. So we could add that as well back up here. And that got erased before. So metamorphism is also taking carbon out of the sedimentary rocks, putting it back into the air. So let's go back to feedback mechanisms. So this is a bit of review from earlier lectures regarding, but we have a little more information now. So the question would be, what stabilizes carbon dioxide long term? Okay, so there's a certain amount of, so we'll draw a causal loop diagram. So we have carbon dioxide in the air, and we know that when that's higher, we have higher temperatures because of the greenhouse effect. So higher CO2, higher temperature, or lower. If we lowered CO2, that would lower the temperature. So that's a positive feedback. And temperature affects weathering for a couple of reasons. Okay, if first of all, the warmer increases the rates of chemical reactions. And also, higher temperatures can lead to more CO2 dissolved in the water, which increases the acidity. So, warmer, faster reactions. So the weathering speeds up. And the acidity increases. So higher temperatures lead to greater weathering. And as I said earlier, the weathering that sort of dominates is the silicate weathering. Okay, so the silicate in particular uses up CO2. So more silicate weathering means less CO2 is in the atmosphere. And so this is a stabilizing feedback loop. And this is thought to be one of the most important ones in terms of keeping carbon dioxide levels relatively stable. So, for example, we could write this down. So, if CO2 got too high, let's say, for example, there's increased volcanic activity. So we get a lot of CO2, it increases the temperature, that causes more weathering, that reduces the CO2, it stabilizes. And you could go the other way too, of course, like all of these. Let's say that there was a lot of continental collisions. So you exposed a lot of rock all at the same time, geologically speaking. So there was a lot of weathering happening that would bring the CO2 down. It gets colder. And that slows down these weathering reactions, which decreases the weathering. So then the weathering is going down. Slower weathering causes the CO2 to go up. Okay, so it's stabilizing. So the final topic I think it's worth describing how we actually measure CO2. So in the air, it's a device. It's like this. There's a light source. And it shines light down two tubes. One has, so the light's going down through the gases. So there's right, we have our sample of air, like our air sample, and we have some reference. And basically we just have a detector, a light detector, that compares how much of the energy reaches the detector. Maybe there's actually two detectors for each tube, right? So because CO2 is a greenhouse gas, depending on how much of CO2 is in here, less light will get through. The more CO2, the less light will get through. So it's interesting. It uses the same principle as the greenhouse effect. We use that in it's called a non-dispersive infrared detection. So they're shining infrared light through here. So let's just write this down. We shine a light through two tubes. One with a reference gas, so nitrogen usually, and one with air. When we measure, compare the intensity of the light. CO2 absorbs energy. So less light hits that detector. And this relies on the same properties as the greenhouse effect.